Those who are online, are you able to hear me?
Yes, sir.
Okay,
Yes, sir.
third with the we'll get started with the next chapter. Right. So, what is the name of the next chapter? It's called electrostatic
Electrostatic potential and
and capacitance.
capacitors.
Right. So, it's called electrostatic potential and capacitance. So, if you look at it, right, electrostatic comes from the previous chapter. That is, we are dealing with the charges which are at rest, right? So, we need to see what this potential actually means. So, potential comes from the energy that is possessed by a body by virtue of its position, shape, or configuration, right? And here the third part that we are going to see is capacitance. So, capacitance is basically the property of a material called as a capacitor. It's not a material, call it as a device. So, property of a device called as a capacitor. That is a basic outline of these three words. So, in the previous chapter, what we did is we had the charges which are placed in different orientations. One thing, we either calculated the force, and the other thing is we calculated the electric field. Right. Now, what we are going to do is we are going to calculate something called as electrostatic potential energy or electrostatic potential. Right. So, these are the values which we are going to calculate and apply it for different systems of charges. Right. And lastly, what we are going to do is we will see how this quantity of electrostatic potential from this chapter is related to the electric field from the previous chapter. So, based on that, we will be deriving some important conclusions, right? So, having said this, shall we get started?
Yes, sir.
So, the first point, the first point that we are going to see is electrostatic potential and potential difference, right? So, here, what it means is, first thing we need to understand when will you use the word electrostatic potential is when you have an absolute value.
Sir.
So tell you, yeah.
Sir, we can't see the screen, sir.
Is it so? Is it visible now?
No, sir.
No, sir.
Is it visible now?
Yes, sir.
Yes, sir. Now it is visible.
Yeah. So, electrostatic potential and potential difference, right? So, when I use the word electrostatic potential, I'm talking about the absolute value. And when I speak about potential difference, I'm talking about the difference between 2 points, right? So, if you recollect, I would have mentioned this important point stating that whenever you talk about electric field is always measured at a point. In a similar way, electrostatic potential is also measured at a point. Right? So, how is it measured or how is it defined is what we are going to see in the first place. So, throughout physics, when you see the word potential, right, or potential energy, the first thing that should come to your mind is work done. Right? So, basically, the potential difference between 2 points in an electric field is defined as the amount of work done in moving a unit positive charge from one point to another against the electrostatic forces. That's what the definition says. Okay, what do they say? If you have to define the potential difference between 2 points in an electric field, meaning there is a region present. In that region, what do you have? You have a charge which is present. You are moving the charge within the electric field against whom? Against the electrostatic forces. So if you are able to do something like this, then you are able to give the material something called as potential energy, right? And if you divide the potential energy per unit charge, that is going to give you the potential. I'll come to it. Okay. First, let's visualize the situation. So I have a charge which is generating the electric field. So let me call this as Q. This is the one which is generating the electric field. And in the presence of this electric field, there is another test charge Q naught. You actually have a unit positive test charge, right? So you have this test charge Q naught. Now, this is positive. This I've considered to be positive. It is my choice. Source charge can either be positive or negative. And tell me what will happen to this test charge due to this positive charge. It will experience an attractive force or a repulsive force. Repulsive force. So if I try to define the direction of force, the electrostatic force is going to be away. But what is the definition saying? The work is not done by the electrostatic force. The work is done by the external force. Right? The work is done by the external force. Meaning, if I have to move this charge Q naught towards the point Q, then I need to do a work against the electrostatic force. So this will be the work done by the external force. Clear with this, right? Now, what I'm going to do is, let us say the distance between the charges initially is x. Now, with the help of this external force, let's say I have displaced this Q naught by a small distance dx. Right? Then, listen to this carefully. When I talk about work done, right, the work done has two formulae. One is F vector dot S vector, or integral of F into dx. We need to know when to use the right one. So if you look at the first one, it is used when the force is constant. When is it used? It is used when the force is constant. This is used when the force is variable. Right? If you see, in this case, what will happen is, if the external force has to exceed the electrostatic force and start moving the object in this direction, the external force is supposed to be slightly greater than Fe, such that F external can be approximated to Fe itself. Meaning, mathematically, we take both the numbers to be the same. See, logically, you tell me one thing. Somebody is pushing in this direction. You need to move the object in the leftward direction. So which force should be more? External force should be more. But in this case, when you do a comparative study between the external and the electrostatic force, the external force is slightly greater than the electrostatic force, where these two can be approximate. Right? Now tell me, what is the small amount of work that is done by the external force through a displacement of dx? It is going to be K Q into Q naught divided by x square, right, times dx, right? So if I need the total work that is done, I need to integrate it like K into Q naught divided by x square into dx. From where to where? I need to integrate it from, let's say, R1 to R2. If at all, I take the first point to be infinity. Infinity means a point which is outside the electric field. Infinity. And if I say the second point is at a distance R. Right? So what I can take out of the integral is KQ into Q naught into integral of dx divided by x square, which is varying from infinity to R. Did you understand the story? Right. Now, this KQ into Q naught, right? KQ into Q naught into integral of 1 by x square is actually going to give you minus 1 by x Integral of 1 by x square is minus 1 by x, and it is going to vary from infinity to r. Okay. Now substitute the limits. So you can take the minus outside. So minus kq into q naught multiplied with, it is going to be 1 divided by r minus 1 divided by infinity, meaning the upper limit minus lower limit. So upper limit minus lower limit. So this will be equal to minus kq into q naught into 1 divided by r. Listen to this very carefully. This is the work done that you have calculated, which you have got as minus kq q naught divided by r, right? This work done is actually going to be something called as electrostatic potential energy. What is it? It's called as electrostatic potential energy. It is not electrostatic potential. There is a slight difference. Electrostatic potential energy is minus kq q naught divided by r. Now, listen to this. I'll give you time to copy. If I am able to calculate the electrostatic potential energy and divide it with q naught, you call it as work done, because potential energy is work done. Work done per unit charge, right? So this will be actually minus kq q naught divided by r, the whole divided by q naught. So q naught and q naught will get cancelled. This will be minus kq by r. This is what is called as electrostatic potential. This is what is called as electrostatic potential. It's not electrostatic field. It is not kq by r square. Here it is kq by r only, no? There is a relation. We'll see it later. I hope you could understand, right? So this is
Yes,
how the
sir.
chapter starts. Not like previous chapter where you have so much of theory and then derivations. Direct attack on integration. Is it clear? Shall I proceed? So listen. When you talk about electrostatic potential energy, it is minus K Q Q naught divided by R. When you talk about electrostatic potential, it is going to be minus KQ divided by R. You can actually ignore the minus sign. Okay. It is okay. Ignore the minus sign. It is written as KQ divided by R. Okay. So here, potential energy is measured in terms of joule, whereas the electrostatic potential is measured in terms of joule per coulomb. Right. So shall I proceed? Okay.
Yes, sir.
Now here I want you to make a note. Here the negative sign indicates that electrostatic force is conservative in nature. Negative sign indicates that the electrostatic force is conservative in nature. No. So open your textbooks. Let's do an example problem based on electrostatic potential energy. Look at example 2.4, which is in page 63. So page 63, example 2.4. So read that question. What is it? There are 4 charges, right? How are they placed?
Corners of a square.
Yes. So there are 4 charges which are placed at the corners of a square. And how much is the value of each charge? So tell me from left hand side. Tell me for this one. Q. And what is the side A? What is the side D? Okay. So the side of the square is D. Now what are they asking? So calculate the amount of work that is needed to be done to bring this kind of an arrangement. So the meaning of it is, listen to this carefully. Assume that the system was completely dismantled. So each charge were lying at infinity, means they were having no connection among themselves. So first what we did is, we brought this charge from infinity to this point. You did some work. So after you place it here, you take this charge, this was at infinity, from infinity you try to bring it here. Will you face some difficulty or not? Why? Because this charge is already there and it started creating some field around, due to which it would have started experiencing some attractive force. So we need to do some external work to overcome that attractive force, right? After you do that, let's say they both are placed at this point. Now what you're doing is the third charge is at infinity. Now you're trying to bring it in the form of a square, like to bring it in the shape of the square. So when you place it here, what will happen? It will experience a force due to these two charges, right? Similarly, this is at infinity, or bring it here. As a result of which you formed a system of this format, right? So when you did all this work, is there not some energy that is going to get stored in it? So what is the energy that is going to get stored in it? It is going to be the electrostatic potential energy. So what is the value of electrostatic potential energy that will get stored in it? It is very simple. It is amount of the electrostatic potential energy between AB, between BC, between CA, and between CD and DA, right? But we are missing two other things. It is between AC and it is between BD also. So what I'm trying to say is, whenever they ask a question based on work done, what you need to calculate is the electrostatic potential energy. For you to calculate the electrostatic potential energy, what is the minimum number of points, minimum number of charges that are required? You need two charges. So what are the two charges? AB is one combination, BC, CD, DA, 4, AC and BD. So there are total 6, right? So for those 6, how you will calculate is, if you observe what is the electrostatic potential energy between AB, it is minus K product of charges. So Q into minus Q square divided by the distance of separation between them. Like that, if you take any two combination from AB, BC, CD and DA, aren't they the product of opposite signs? So this whole thing will get repeated 4 times. Makes sense? Plus, if you take UAC and UBD, when you multiply A and C, they are two positive charges. When you multiply B and D, they are two negative charges. So you will get 2 times minus K Q square divided by, what is the distance of separation between them? What is the diagonal of a square? Root 2D. Right, Pythagoras theorem. D square plus D square under a root 2D. Right. So what is going to be the final value? Can I take this KQ square divided by D outside? So minus of minus plus, and I have a 4. So I have a 4 here. Minus, I have 2 divided by root 2. So what will it be? So this will be the answer. So this is the amount of work that we need to do to arrange this kind of a system. Am I clear with this? Clear with this? So what is the next part of the question? What is the next part? What are they asking? So before that, did they ask only about the work done? Did they ask anything about potential? No, right? Okay. See, at the center, okay, let me call that as O. If I extend the question saying, find the potential due to the system at point O. Find the potential due to the system at point O, then what is it going to be? It is going to be the potential due to the charge at A plus the potential due to the charge at B plus potential due to the charge at C plus the potential due to the charge at D. So, how much is this distance? How much is this distance? Where? Minus of minus, I took plus. So that one is 4. Got it? Okay. So VA plus VB plus VC plus VD. So what is the potential due to the charge at A at point O? It is going to be KQ divided by, what is this distance? See, this whole distance is root 2D. So how much will this be? It will be D by root 2. So KQ divided by D by root 2 plus, what is the potential due to the charge at B at point O? It will be K into minus Q divided by D by root 2. Why did I put a minus sign here? Because I'm dealing with a scalar quantity. So whenever you're dealing with a scalar quantity, you need to put a minus sign. Plus potential due to the charge at C. It is KQ divided by D by root 2 plus, what is the charge here? Potential due to the charge at this point. K into minus Q divided by D by root 2. So what will answer be? The potential at the center is 0. The reason why I did this is because, what is the next part they have asked? They told you bring an extra charge Q to the center of the square. What is the extra work that you need to do? So to calculate that, what you can do is, calculate potential at a point, right? Calculate the potential at a point and multiply with the charge. Calculate the potential at a point and multiply with the charge. So what is the potential at point O? It came out to be 0. What is the charge that you're trying to move? Q. So work done will be equal to Q into V naught. So it is 0. Means you need not do any extra work to bring the charge from infinity to that point. So there is the answer. Is the point clear? Here. So these are the steps that we need to follow whenever you're asked to calculate the extra work that is done. Okay. Now, shall we do some problems based on potential? So, you understood both the formula, right? Now, go to 2.1. Look at example 2.1. So, example 2.1. So, what does the question state? There will be two charges, right? What does it state? So, what are the two charges that are present? Oh, this is not the one. Okay. Calculate the potential at a point P due to a charge 4 into 10 power minus 7 coulomb located 9 centimeter away from it. So, what are they saying? There is a charge whose value is 4 into 10 power minus 7 coulomb. And due to this charge, we need to calculate the potential at point P. Right? If I take this distance to be R, for instance, what is the potential at point P? It is going to be KQ divided by R. So K is going to be 9 into 10 power 9 into Q is 4 into 10 power minus 7 divided by R is how much? So 9 and 9 will get cancelled. So you will be left out with 4 into 10 power 2 into 10 power 2. So it is going to be 40,000 volt. That's sorry, I forgot to tell this. The joule per coulomb is there, no. The joule per coulomb is actually volt. So joule per coulomb is volt. So answer will be 4 into 10 power 4 volt. Okay. Next, what is there? So work done to move a charge of how much value? 2 into 10 power minus 2 R. Minus 9 coulomb from infinity to point P. So what will you write? Work equal to the charge that you moved multiplied with the potential of point P. That's it. So the charge that you moved is 2 into 10 power minus 9. What is the potential at point P? 4 into 10 power 4. Answer will be 8 into 10 power minus 5. So 8 into 10 power minus 5 joule. That will be the answer. Clear with this? Right.
Yes, sir.
Yeah. So what is the next problem they have asked? So I think this one is done. Right. What about 2.2? What is that? Does the work depend on the path along which you brought the charged particle? The answer will be no, because electrostatic forces conservative in nature. Does not minus component there it represents, but electrostatic force by default is conservative in nature. See, because here the work is done by the electrostatic force, so it is going to be conservative in nature. Electrostatic force by default is conservative in nature. Like how gravitational force is conservative, electrostatic force is conservative, and conservative forces, work done by the conservative forces are path independent. It does not depend along the path which you move the objects. So work done by conservative force are path independent. Okay. Next. So look at example 2.2. What does it state? So this is an important question. Okay. See, two charges, 3 into 10 power minus 8 coulomb and minus 2 into 10 power minus 8 coulomb are located 15 centimeter apart. Positive, negative. 3 into 10 power minus 8 coulomb and minus 2 into 10 power minus 8 coulomb. These two are located how many centimeters apart? They are located 15 centimeter apart. Okay. At what point on the line joining the two charges is the electric potential zero? Take the potential at infinity to be zero. Okay. So it says for this kind of a system, on which point or points, right, along the line joining these two charges is the electric potential zero. Right. So what I'm going to do is, I'm going to take a point here. If I take this as A, right? So what is going to be the potential at point A? It will be the potential due to the first charge plus the potential due to the second charge. If I take this to be the first, this to be the second. Okay. Let's say from the first charge, let me call this distance as R. Am I clear? I'll call this distance as R. So what is the potential due to the first charge at point A? It is K into 3 into 10 power minus 8, the whole divided by R, plus K into minus 2 into 10 power minus 8 divided by (15 plus R). So according to the question, what is the potential at this point supposed to be? It is supposed to be a 0. So what will happen is this K is something that you can cancel off. 10 power minus 8 is something that you can cancel off. So you will be left out with 3 by R is equal to, take the value to the other side, you will be left out with 2 by 15 plus R, cross multiply. 45 plus 3R is equal to 2R, which implies 45 is equal to minus R. Okay. But this answer is wrong, because this R you have taken, no, distance, not displacement. So distance cannot be negative. Right? So since distance cannot be negative, we can say that this is not possible. Having said this, then the other point that I'm going to consider is, I'll draw the diagram again. This is case number 2. I'll take the point P here, okay, where the potential is 0. Let me call this as R. Then this is going to be how much? This distance is already 15. So it is going to be 15 minus R. And this is going to be 3 into 10 power minus 8. And this will be minus 2 into 10 power minus 8. Am I clear with this? Right. So again, the first charge, second charge. So potential at point P will be equal to potential due to the first plus the potential due to the second. So what is the potential due to the first charge? It is going to be K into 3 into 10 power minus 8 divided by R plus K into minus 2 into 10 power minus 8 divided by 15 minus R. This is going to be equal to 0. This is supposed to be 0. All right. So K and K are gone, 10 power minus 8 and 10 power minus 8 are gone. So when you cross multiply, you get 45 minus 3R is equal to R. Okay, you take this value to the other side. 45 minus 3R will be equal to R. This will be equal to, or this will imply 45 is equal to 4R, or R will be equal to 45 divided by 4. How is it 9? Yeah, 11 point something. But 1 minute. All right, 3 into 10 power minus 8 divided by R minus 2 divided by. So 45 minus 3R is equal to, no, here it is minus 2R. Not minus 2R, the plus R, plus 2R only. So that, yeah, now 9 is correct. But how did you get that 9? Book it's there. Huh? Wait, I'll explain these steps again. So listen, there is a correction. So when I cross multiply, we get 45 minus 3R is equal to, this 2 is there, no, 2 will get multiplied with R, it will be 2R. So 45 will be equal to 5R, which implies R is equal to 9 centimeters. So when you're reporting this answer, no, you should not write it as 9 centimeter in length. You need to mention it is at a distance of 9 centimeter from the charge of value 3 into 10 power 8. Sorry, 10 power minus 8. You need, whenever you are reporting the distances, right, you need to mention the reference point, because one of you might write it as 9. If someone has taken R on this side and 15 minus R on this side, they would have got the answer as 6. So which one will you consider it as right? You can take either of them to be right, provided you mention the reference point. 9 centimeter from the positive charge or 6 centimeter from the negative charge. If you don't mention that, you're done. You lose marks there. Am I clear with this? So it is 9 centimeter from positive charge. Am I clear with this? Did you understand why this is wrong? Because here the distance can't be negative, whereas here you got a positive value. Yes, it is right. So let me complete, then you can copy it. Okay. The next scenario is, going to be like this. Positive charge, negative charge. So it is going to be 3 into 10 power minus 8. And here it is minus 2 into 10 power minus 8. Let me consider the point to be here. Let me call this as P dash. I'll take this distance to be R. Then this distance will be 15 plus R. Clear with that? Right. So what is the potential at point P dash? So it is going to be the potential due to the first charge plus the potential due to the second charge. What is the potential due to the first charge? It is K into 3 into 10 power minus 8, the whole divided by 15 plus R plus K into minus 2 into 10 power minus 8 divided by R. How much should the value be? 0. So K gets cancelled, 10 power minus 8 gets cancelled. So when this minus 2R, 2 by R goes to the other side, it become plus 2 by R. Cross multiply. 3R will be equal to 15 into 2 is 30 plus 2R. So take the 2R to the other side. R will be equal to 15 centimeter. But remember, this time the R is measured from the negative charge. So R is equal to 15 centimeter from negative charge. So if you observe, what are the two possible scenarios? It is at a distance of R is equal to 6 centimeter from negative charge. See, it was 9 from the positive charge, 6 from, oh sorry, R is 30. Okay. So I have to come from there again. So R is equal to 30 centimeter from negative charge. Right. Now, if you observe, the two scenarios is you either got R is equal to 6 centimeter from negative charge or 9 centimeter from positive charge. That was one of the scenarios which was in between the charges. And the second case is you got R is equal to 30 centimeter from negative charge or 45 centimeter. Why 45? It is getting, the 15 is getting added from positive charge. So if you observe in both the scenarios, where is the point where the potential is 0? It is always away from the positive charge in this case and closer to the negative charge. Is it going to be the scenario every time? No. It will change according to the magnitude of either of the charges. So listen to this very carefully. Next time, right, you need not sit and do all the 3 cases. You can do only 2 cases. So those 2 cases will be in such a way, one will be in between and one will be on the side of the charge with lower magnitude. I'm stressing on this point. One will be on the side of the lower magnitude. Why I'm using this word magnitude is because what is the magnitude of this charge? 3. Here the magnitude is 2. For example, had the question been this as minus and this as plus, still the points would have been here only. Here, listen to this carefully. Had the question been instead of this being minus 2, had this been negative, this been positive, still the points that you have considered, still you would have got the same answers only. Why? That is how this potential at a point being 0 works. So where will it be? It will be either in between the charges or on the side of the charge where the charge has the least magnitude. That is one thing. And secondly, you will have the potential at point P to be 0 provided in the question you have the charges of opposite nature. Had the question been in such a way that both the charges had like nature of charges, had they been of like nature, right, you would have never found the point where the potential is 0. You got the answer to be 0 only because of this minus sign. Mathematically, you can take it to the other side. Are you able to understand? These are all the points that you need to observe. Why I'm telling is next time you need not sit and solve this much. Am I clear with this? So what is the point I told? Potential at a point will be 0 and the point will be close to the charge with completed least magnitude. Yeah. It will be closer to the charge with the least magnitude. Clear? And this is a very, very important problem. And in exercise also, the first problem is based on this concept. I want you guys to try it on your own. You can do it as homework, but do it on your own. In exercise, the first problem. I think they're asking, where is the potential zero? Right? Yeah. I'll show. So I'll go to the previous slides. You can make a note of. Yeah. Here, Radha. You are with this? Yeah. So I think the next slide you can do it on your own. I didn't put that. That is the third case. The one which I wrote on left hand side. This one, huh? Okay. Sure. So with this, we have come to the end of today's session. Okay. So as I told you on 17th, I'm not there. I have some travel plan. So on 17th, by today itself, you will get the pre-recorded videos. So go through the content and come to class so that we can concentrate on problems like this. Okay. But only thing is, I'll put a rule like this in the assignment tab. I'll be creating an assignment where you need to write the notes and upload your notes there for me to check whether you're doing it or not. Or else if you come under-prepared to class, that class will be held. If you forget to see the video and come to class and you see the problem, you'll go. Okay. So it's better you go through them. I'll tell you what topics you need to go through also. You just go through and work out and come. So on 18th also, I'll start doing problems like this. Okay. So are there any doubts?
No, sir.
Any questions? Those are online, any questions?
No, sir.
Okay, shall we wind up?
Okay, sir.
Yes, sir.
Okay. Okay. I'll see you all on
Thank you,
18th.
sir.
Thank you, sir.
Thank you, sir.
Yeah.